Good afternoon, students. So the last lecture we were looking at the example for calculating the CRC. Of course, we were rushing through it. So let me once again explain the remainder calculation before we proceed to the new topic. Okay. So basically the sender. So there is a sorry. There's a sender. There is a sender S. Okay. So this sender has a message M. Okay, in polynomial we can represent this as m of x, and this also uses C, that is the divisor C, and it's going to transmit what is called P of x. So this P of x is nothing but M followed by R. M is the message bits, okay, R represents the remainder bits, okay. C is the divisor. So we take an example. Let's say M is an 8-bit binary number, okay, and C is a 4-bit binary number. So this is basically x cube plus x square plus 1. That's what the divisor C represents. Okay. So what we do is, the first step, we append M with k zeros. So k zeros. K here is 3. Why k is 3? Because k represents the degree of the polynomial, the divisor polynomial, which is 3. Okay. So first step is add 3 zeros, k number of zeros with M. So this adding 3 zeros at the end, okay, here, which we call it as t, which is the same as multiplying by x raised to the power k. Because when you multiply it by x raised to the power k, this is equivalent to shifting towards left by k bits, whether it's in decimal or base 2, similar in the case of this polynomial. Okay, so that is what is given here. So this is basically t, this is t. Then we use the divisor 1101 to divide. Okay, so as I said before, don't look at the magnitude. So you just imagine this is a polynomial. So what we are interested in is, there's a 4 terms here. So we are interested in the 4 terms. As long as there are 4 terms, okay, with the most significant term is 1, okay, we can proceed with the division. So division, this is 1, 1101, and we are going to subtract. The subtraction is based on modulo 2 arithmetic. Modulo 2 arithmetic is basically exclusive OR operation. So 0 minus 1, 1. There is no borrowing, there is no carry, there is no borrow, anything. 1 minus 0, 1. Then 0 minus 1, 1. So now we have 3 bits, 1, 1, 1. So bring the next bit 0 here. Now make it 4 bits, 1, 1, 1, 0. This is 1, 1, 0, 1. So there are 4, because there are 4 terms here, 4 terms here. So 1, 1, 1, 0, 1. Now you get 0 minus 1, 1, 1 minus 0, 1. This is 1, 1. Now we have only 2 bits, so we need to bring the third bit. We cannot divide further, so put a 0 here in the quotient. Bring one more bit, 1. Then you put one more 1 here. So now it is 1, 1, 0, 1, 1, 1, 0, 1. Okay. So when you subtract, again you get 2 bits, 1, 0, 1 minus 1, 0, 1 minus 1, 1. So again bring 2 more bits. Then there's another 1. So 1, 1, 0, 1, 1, 1, 0, 1. So note that, okay, this 1, 0, 0, 1, 1, 0, 1, okay, in terms of magnitude, this 1, 0, 0, 0 may look smaller. But as I said before, don't look into the magnitude of the number. Just look at whether it has 4 terms or not. That's all. So if you proceed further down, at the end of the division, you have 1, 1. You make it a 3-bit remainder, 0, 1, 1. Okay, we make it 3-bit remainder because the divisor polynomial has 4 terms. The remainder will have 3 terms. Maybe in a conventional decimal, if you divide a number by 5, you will get maximum 4 as the remainder, either 0, 1, 2, 3, or 4. Okay, if you divide a number by 7, you can get a remainder up to 6, 0 through 6. So here, if you divide by a 4-bit 4-term polynomial, you will get a 3-term polynomial. Is that fine? In other words, here the degree is 3, here the degree is 2. Okay, so next step is this. So now the 0, 1, 1 is the remainder. The polynomial which is transmitted as p, this is nothing but p is equal to m minus r. Sorry, t minus r. What is t? T is this. What is r? This. So this minus this. That means the last 3 bits are 0, 0, 0. Here the bits are 0, 1, 1. So when you subtract 0, 1, 1 from 0, 0, 0, you will get the same 0, 1, 1. Is that fine? So you don't need to actually subtract, even though in terms of operation we say. So what you can do is you put this. This is m, just append it by r, followed by r. That's all. Is that fine? So this is what is transmitted here, but what is received at the receiver need not be exactly this. So if you look at our previous example, for the analogy, that is 27.2, which is transmitted by the sender. When it is received by the receiver, it could receive 27.2 or 26.2, okay, or just an example, okay, or it can receive, let's say, 37.2. That means during propagation, the numbers may be changed. Is that fine? So similarly here, when this is transmitted, so this, okay, this is what is transmitted, some bits may be affected due to the error. So in that case, we say that the received polynomial is p of x plus e of x. E of x is the error polynomial. Error polynomial can be 0, no error, or it might have some terms that indicate that the corresponding bits have been damaged. Is it okay? So now what the receiver will do is it will take whatever it has received and it will divide entire thing by the remainder, sorry, the division polynomial. It will check the remainder. If the remainder is 0, then there are 2 cases. If the remainder is 0, that means there is no error. That, I mean, if there is no error, okay, in that case also the remainder will be 0. There is another case, the remainder will be 0 when the error polynomial is exactly divisible by c of x. That is, when 27.2 is received as 37.2, here the error is 10. The difference is 27, 37, the error is 10. So if, okay, 10 is, because here 10 is divisible by 5, there is a confusion, okay. So if the error polynomial is divisible by the division polynomial, then the receiver will think that there is no error, but actually there is an error. So we say the error goes undetected. So we need to carefully choose the divisor polynomial. Okay, again, the example of this 27.2 divisor 5, this I gave only for the analogy illustration purpose. Okay, but in case of CRC, the divisor polynomial is not quite straightforward. Okay, we cannot choose any polynomial as divisor polynomial. We want to choose divisor polynomial in a way that it can detect many possible errors. Of course, we cannot come up with any polynomial which can detect all possible errors, but many possible errors could be detected. So there are theorems governing the selection of the divisor polynomial. We are not going into the details of those theorems and proof. Some time back I used to teach some proof, but now there are other topics to cover. Okay, we skip all the mathematic theory proof and all, but just note some key points. How we are going to select the divisor polynomial c of x. So c of x, let's say with degree k. That means the polynomial should be x raised to the power k plus x raised to the power k minus 1 plus 1, something like this. Okay, the first theorem or fact, what it states is this: all single bit errors can be detected as long as x raised to the power k and x raised to the power 0 terms are present. That means if the divisor polynomial has some terms something like this and 1, then it can detect all possible single bit errors. Assuming that there is only one bit which is corrupted, then it can detect that error. It can detect. It doesn't know which bit has been corrupted, but it can tell yes or no. Okay. Similarly, any odd number of errors can be detected. What do you mean by odd number of errors? Let's say 1 bit is damaged, or 3 bits, 5 bits, 7 bits, even 101 bits. If any odd number of bits are damaged, or odd number of errors occur, that means odd number of bits are damaged, this can be detected if C of x, which we choose, contains the factor x plus 1. That is, factor x plus 1 means C of x divided by x plus 1 should give remainder 0. Should give remainder 0. Is that clear? Got it? Any doubt? Any doubt? Okay. So how do you check? Suppose in the test or anything, if I give, okay, this is the polynomial, divisor polynomial. You are asked to check if it can detect any odd number of errors. So what you should do? You should check whether it has a factor x plus 1. How do you find whether it has a factor? You have to divide it by x plus 1 and you should see whether it gives remainder 0. But again, carrying out division in polynomial is difficult. Even though here we say x power 7 plus some polynomial, actually in the two polynomial here it can be plus or minus. Okay? So don't carry out any division in the polynomial. Better you carry out the division in the binary. Put the polynomials in binary form, then divide. How you know how to divide? Am I correct? Okay. Any burst error of length k, burst error means consecutive bits are damaged. Let's say if k is 32, if 32 bits are damaged continuously, it can be detected. And in most of the cases, even if the burst error is longer than k bits, it could be detected. There are some standard polynomials which are in use by the network community. Okay, there are many different polynomials possible. Okay, because they are standardized. For example, you take CRC 32. CRC 32 means it's used in Ethernet. That means if you look at the Ethernet frame format, at the end you will see CRC. So this CRC is 32-bit long. Okay, so CRC 32 means it should have 32 remainder bits. CRC bits means 32 remainder bits. So 32 remainder bits means the polynomial should start with x power 32 plus 1. We are not looking at the exact polynomial, but I just say the degree should be 32. So x raised to the power 32 plus some terms will be there. Some terms may be missing, but x power 32 and x power 0, that is 1, should be present. Okay. If you are interested to look at what these polynomials are, you can see any book or any web resources. So it will give you the polynomials which are recommended to be used in the networks. Okay. We are not here to memorize those polynomials. We are interested to know the concept behind this. So later in the tutorial, not today, maybe Wednesday, we will look at some problems which will help you better understand the CRC at the sender as well as the receiver. Okay, let's move on to the next topic, lecture notes 4. This is on flow control and reliable transmission. Okay, so this flow control and reliable transmission are the key functions which are carried out at both connection level, end-to-end, as well as link level. So here we mainly focus on the link level. That is, link means which connects two nodes, router, switch, or node, host, switch, etc. Okay. So the reference book which I follow here is by William Stallings. Okay. There could be different editions. You can follow any edition. I don't see much difference. Okay, but again, this does not mean that other books are not good or something. Okay, other books also talk about the same topics, similar concepts. They cannot, but the way they present the examples could be different. Okay, so whether you follow my notes or this book or the other book, doesn't matter. I leave it to you. Whichever you find it interesting or you can easily follow it, you can follow it. Yeah. So what's a flow control? Okay. Now let's look at a link connecting a sender and a receiver. This is the sender. and this is the receiver. Or you can consider a connection which passes through multiple, one or more links. So this is, let's say, the source host, and let's say this is the destination host. Okay, maybe let's call it this as A, this is B. So here let's say S and D. Okay, let's consider two nodes which are connected by a direct link or by a connection which can traverse one or more links. Okay, in both cases the concept is the same, but the technique or protocol may have some differences, but underlying concept would be the same. Okay. Now the question is, what is flow control? Okay. Now this should not be confused with congestion control. Later in the tutorial we look at some interesting worked out example to differentiate congestion control and flow control. But the meaning is this, as the name says, okay, whether the flow, the traffic flow, okay, and the speed of traffic flow, okay, would it affect the receiver or not? Okay. For example, let's say there is a sender A which is transmitting frames. Here the packets means frames. Okay, so sender A sends frames to B, frame 1, 2, 3, 4, 5. Okay, so this is going through a link which is connecting A and B. The link might have sufficient bandwidth. Let's say it's a high bandwidth link. Okay, if A can transmit 1000 frames per second, all these 1000 frames, okay, can be carried out by the link bandwidth, link capacity. There's no problem. Okay, so all 1000 packets reach B safely. Is that okay? Through a link or a connection. But if B is slow, the receiver is slow compared to sender. What do you mean? Let's say the sender is transmitting 1000 packets per, let's say, second, okay, or per minute, whatever it is, sometimes time scale, okay. So the sender transmits 1000 packets, 1000 frames per time unit. The question is whether the receiver B can process those 1000 packets in one time unit. If B cannot cope up with A, it cannot process 1000 packets in one time unit, that means B is slower when compared to the sender S, then there's a chance that B may skip or drop some packets. This is the example I used to give every class. Okay, let's say I'm the sender. Okay, I read out some statements. Okay, and I ask you to write it down. I ask you to write it down. So you are the receiver. I am the sender. Okay, so since I am reading, I am faster than what you are doing because you are writing it. Am I correct? So I read the first sentence. I read the first sentence. You hear it, you can write it. Okay? But let's say I increase my pace. I'm reading first sentence, second sentence, third sentence. So what happens after some time? You'll quickly, maybe you try to improve your speed of writing, okay? But at some stage you may not be able to cope up. I'm becoming faster and faster. So you can hear it. Whatever I speak, you can hear it. There's no problem. It reaches your ear, but you cannot process it. You cannot process it inside. Am I correct? So you write one sentence, two sentences, then suddenly you might miss out. Better, let's say you may miss third sentence, maybe, but you can remember the fourth sentence. Maybe you may write the fourth sentence. Am I correct? So if the receiver is slower when compared to the sender, okay, then we say that the sender is jamming the receiver, and the receiver is not able to cope up with this. This leads to what is called the flow control problem. Okay. Usually the receiver has some buffer for flow control purpose. Okay. So even if the sender is faster, some it can buffer. Okay, as long as the buffer can hold. Okay. Beyond that, it has to drop the frames. Okay, it's a potential issue. This is something like I read first sentence, second sentence. Some sentences you can keep it in your buffer. Am I correct? Oh, Prof said this sentence. Yes, this sentence. But if I keep on giving more and more uh, sentences, then you cannot store, remember all those sentences. Am I correct? You start missing some sentences. Is that fine? Okay. So flow control is a technique used to ensure that a sender does not jam or overwhelm the receiver. So we have to make sure that sender is not jamming the receiver. Okay. So as I said before, the receiver has some buffer of finite size to cope up with the sender. Okay. But flow control should make sure that the buffer does not overflow. The buffer does not overflow. Okay. It should not be confused with congestion control. Okay. Okay. Flow control concerned only two parties, sender and receiver. It's not involved in any of the intermediate links or routers, this. Okay. But congestion control, okay, deals with multiple senders, multiple receivers. They are all trying to go through one particular output port of a router, okay, where the sum of the input rate exceeds the output rate, then there are excessive bits at the router, switches, or whatever it is. That's a different problem, okay. So later in tutorial, I'll give a better example to differentiate. So at this stage, you should know that flow control is concerned with only two nodes, sender and receiver, not at the intermediate nodes. Okay. As I said before, this problem exists in layer 4 also. That is, for example, you take TCP at layer 4. So flow control and also the reliable retransmission, they are taking place at layer 4. Okay, so layer 4 does that. At layer 2, it could be optional. Error detection is done, okay, but flow control could be optional and retransmission could be optional. But we will look at the techniques. The optional means some implement, some do not implement, does not matter, okay, because even if some packets are missing, frames are missing, at the end host layer 4 level, there is another person who takes care of this. TCP can take care of it, even if at a link something is missing. Is that okay? But if you can do retransmission or flow control at the link level itself, it eases the burden of the TCP. Okay, so we are going to consider these two models of transmission when we look at some protocols to deal with this flow control or error control problems. So if you look at the first one on the left hand side, okay, so this is basically a timeline diagram. So the time goes from top to bottom. So this is a source. So source transmits frame 1. Then it takes some time to reach the destination. Then it transmits frame 2, which is received by the destination here. Okay. Then you can see that frame 1, the transmission between frame 1, frame 2, sorry, the time between these two need not be the same. Sometimes frame 1, frame 2 may be continuously transmitted. Sometimes there may be a gap. Okay. See, for example, the sender is not ready with the new frame, so it has to wait. Okay. And look at this case. This case is the case with errors and losses. So source transmits frame 1. You look at the frame 2. Frame 2 is lost. This is lost. And you look at frame 3, frame 4. This is the case of damaged frame. So what is the difference? Damaged frame means a frame is received here. That means somehow the frame bits are received and it goes through CRC cyclic redundancy check failed. Okay, because when the receiver divides by the divisor polynomial, it doesn't get zeros the remainder, so it signals an error. Okay, that's a damaged frame. Lost frame means pictorially we show that it has not yet reached the destination. Okay, that means during the propagation through the communication medium, okay, the frame is heavily damaged by a noise, heavily damaged, such that, okay, whatever bits and signals, small signals received at the other side, okay, cannot be even seen as a frame. Okay, this even the receiver cannot apply CRC, okay? It doesn't see a proper frame, okay, because it was heavily damaged. So we call this as loss, okay? That means there is no question of applying CRC there. Okay, we are going to look at two flow control methods. One is stop and wait, the other one is sliding window based. Okay, stop and wait is the simplest of both. As of course, in your lab assignment, you are going to implement a stop and wait based method. Okay, it's very simple. Okay, I don't want to give you a very complex method for the lab because it's an introductory lab to get introduced to use of circuit programming and do some performance analysis. Maybe next semester there's another course, protocols, network protocols course, so where you can do more lab assignments. Okay, but carefully listen through this. It's a very interesting topic, flow control and also error control. And this, okay, whatever you learn from here, it will also be useful for TCP, because TCP is also going to do similar flow control and retransmissions, etc. There are differences. Okay, maybe at link level we work in terms of frames, at connection level we work in terms of bytes. Okay, so there are some differences, but the underlying approach, okay, would remain the same. Okay. So what is stop and wait? Again, you consider two persons, sender and receiver, or source and destination. Source transmits a frame, okay, but source does not transmit the next frame immediately. What the destination does is, the destination receives a frame and it replaces with an acknowledgement. It replaces with an acknowledgement, ACK. Is it clear? Then source, what source does it wait for an acknowledgement before sending the next frame? Very simple. Sender or the source transmits frame number 0. It does not transmit the next frame immediately. Instead, it's waiting for the acknowledgement from the receiver side. So sender waits, transmits 0, waits for the acknowledgement. Once acknowledgement is received, okay, it confirms that the previous frame has been received correctly. Then it transmits frame number 1. Again, it waits for the acknowledgement. Okay, once acknowledgement is received, frame number 2 waits for an acknowledgement, etc. Very simple. So what the receiver or destination does is, whenever it receives an acknowledgement, okay, whenever it receives a frame, okay, it replaces with an acknowledgement. Hi, yes, I have received it. Okay. In case of error, that means if CRC detects an error, it will deal with it differently, that we will consider slightly later. Assume that there is no error, then the destination will immediately send an acknowledgement to the sender. Okay. Again, if you take our example, this is something like, I read out a sentence, I ask you to write. You are a bit slower in writing compared to reading. Am I right? So once you are done, you will acknowledge it, raise your hand, okay? Then I understand, okay, you have written it. Then I read out second sentence. Okay, then I wait for the acknowledgement from you. Are you done? Yes. When you say yes, then I will read the third sentence. Very simple, okay? There's no flow control issue. Am I right? I'm not jamming you because I just read one sentence, ask you to write it down. Only after I get an acknowledgement, I'm reading out the next sentence. So you will not miss out anything. Is that fine? Okay. Now, this is wait because sender is waiting. Stop means the destination or the receiver can stop the flow of packets, flow of frames by not sending an acknowledgement. Okay. So if for reasons, let's say the receiver is not ready, okay, if the destination is not able to cope up with processing of the frames, then it has to stop. It has to stop transmission. It has to request the sender to stop. What it can do is, it simply keeps quiet. It doesn't send any acknowledgement. If it does not send any acknowledgement, obviously the sender will stop. Right? I read out a sentence. You don't acknowledge that you are done. Okay? Then I will wait until I get an acknowledgement. So this is the reason why we call this as stop and wait. So very simple reason. So what is the advantage here? Very simple implementation. implementation is very simple. What's the drawback here? How about the resource usage, efficiency, link usage? The sender sends a frame. Until it gets an acknowledgement, the link is idle. It's not transmitting any new frame. The transmitter is idle, link is idle. So we say that bandwidth utilization is poor because there's long waiting time here and there. Got it? Okay. Now, here we say that, okay, there is frame 0, frame 1, frame 2. But there's a reason why we divide the data into multiple frames, which we briefly mentioned before. Let's revisit it. Large block of data may be split into smaller frames or packets, whatever it is, for the following reasons. Okay, the question is this: why I should not send a big, let's say 1 MB or 10 MB image or file as a single packet or as a single frame? Why I should divide this into small frames? Okay. So what are the reasons? One, limited buffer size. Because you take store and forward switch or anything, okay, or normal statistical TDM based routers or switches, the packets are stored in the buffer. If your packet size is quite long, 10 MB, 100 MB or something, it cannot, very difficult to hold multiple packets in the queue. Okay. So it's better to have a small packets. 2, errors detected sooner. If you look at CRC, okay, to detect whether there is an error or not, you have to divide all the bits. You have to divide all the bits. Am I right? So if the frame size is very long, then it takes more time to carry out the division. The error detection will be longer, the error detection time. If the frame is short, it can quickly detect the error. Am I right? If it has 1000 bits, you just imagine how much time is required. If it has 10,000 bits, the time required would be more. Is that fine? In fact, there is a hardware-based mechanism to calculate the CRC, because if you look at the division process, okay, you see that there is an exclusive OR operation, and there is a shifting. There's a shift. You move the bits. Am I right? We are moving the bits, and also we are doing this exclusive OR operation. So we can design the CRC divisor by using a shift register and also some exclusive OR gates. It's not so difficult to design such things. So if you have such design, hardware design, when the bits go through the shift register, okay, automatically it will go shift and the exclusive OR operations will be done. When the last bit is done, transmitted, the shift register will have the remainder. Okay, it's not carried out as a program or software. Okay, CRC can be carried out in the hardware. In the past, I used to teach the design of the hardware, shift register based design, but there are many new topics to teach, so we skip the hardware design. Okay, you just need to know how the division is carried out. Okay. Then another very important point is that on error, retransmission frames are smaller. Okay, you take 1000 byte frame, you take 10,000 byte frame, you take a 1000 byte frame. Let's say one bit is corrupted. When the receiver says, okay, this frame is a useless frame, one bit, some bits, it doesn't know how many bits are corrupted. Okay, so it's a damaged frame. It's a damaged frame. What should be done? The receiver will drop the frame. Maybe it can request the sender to retransmit it again. So retransmission is done for a 1000 byte frame. 1000 byte frame is retransmitted. If we transmit a bigger frame, let's say 10,000 byte frame, what happens? When the 10,000 frame is received, only one bit is corrupted, but still the receiver has to throw. Receiver has to throw away 10,000 bits. Am I right? So it has to request retransmission of 10,000 bytes. Okay. Earlier it was small. The retransmission is only for 1000 bytes. Now retransmission is 10,000 bytes. So when you retransmit 10,000 bytes, we need to use the bandwidth for transmitting the entire 10,000 bytes. It's a bandwidth waste. Is that okay? Something like you buy a milk, okay, 100 milli, 1 liter. If the milk is spoiled, 100 milli milk, 100 milli milk is thrown. You get a new 100 milli liter. Okay, if you buy 1 liter milk, if it's spoiled, you have to throw the entire 1 liter milk. There's no other way. Okay. Then in case of MAC, this is for MAC, broadcast network. It prevents one station occupying medium for a long period. Okay, when there's a MAC, when there's a broadcast medium, when more than one try to transmit, okay. So let's say one is successful, it's transmitting the frame. Normally, as soon as one starts transmitting, okay, others, if they know about transmissions, they will not stop it. It will complete its transmission. Okay. So if the frame size is very big, then one user will use the medium for longer time. Okay, other people may have to wait. So it may not be fair. So if we need to transmit large number of frames, stop and wait becomes inadequate. If we need to send only small number of frames, it's fine. Is that clear? Any doubt? Any doubt? So the next topic is sliding window based flow control. So what is the drawback of stop and wait? In stop and wait, the sender has to wait for every frame acknowledgement. If sender transmits frame 0, waits for an acknowledgement. Frame 1 waits for an acknowledgement. So there is a long waiting time. Okay. So how much is the waiting time? After last bit is transmitted, the last bit should go to the other side, and the receiver has to transmit an acknowledgement. That acknowledgement has to come back. So during that period, round trip time period, so nothing is happening. Is that fine? So now the question is, why should the sender stop transmitting? Should wait for the acknowledgement. Okay. So can it transmit more than one frame at the same time? Sorry, without waiting for an acknowledgement. Same time it cannot happen. Okay. So on the other extreme end, what can happen is sender does not need to wait for any acknowledgement. It just waits for acknowledgement for the last frame. Let's say it wants to send 1000 frames. Similar example we have seen in tutorial 1. Okay. So sender can transmit frame 0, 1, 2, 3, 4, 5. Continuously it can send. It doesn't wait for any acknowledgement. After transmitting the last frame, only then it waits for the acknowledgement to mark that everything is done. Okay. So here, yes, there's no bandwidth waste because it's continuously using the link for transmission. But the problem is it might lead to flow control. It transmits 1000 frames one after another. It does not even know whether these 1000 frames can be processed by the other fellow. Okay. Is that okay? So the receiver might have dropped few frames. You may not know. Only at the end it will know that it's not acknowledging. So now we devise a strategy which is in between. That is called sliding window. Slowly you will understand why it is called window or sliding window. Okay. So the key idea is this: allow multiple frames to be in transit to improve link utilization. That means instead of restricting the sender to wait for an acknowledgement for every frame transmission, okay, so we are going to relax that constraint. How we are relaxing is that, okay, sender is allowed to transmit up to certain number of frames before, even without waiting for the acknowledgement. Let's say sender can transmit up to 7 frames without waiting for an acknowledgement. If it does not get acknowledgement even after transmitting 7 frames, then it has to wait. Is that okay? Now, how we choose how long is, okay, that's defined by a window. We assume that there is a window of size W. This is a window of frames which could be transmitted without waiting for an acknowledgement. So we say that transmitter can send up to W frames without waiting for an acknowledgement. In the earlier case, stop and wait, this W is 1. Okay, sender is permitted to transmit only 1 frame. Okay, then it cannot proceed until it gets an acknowledgement. Now it can send up to W frames. Okay, then only after W frame transmissions, if it doesn't receive acknowledgement, it will be forced to wait. Okay. Now, because it is allowed to transmit more than one frame without waiting for an acknowledgement, now these frames need to be numbered. We should say frame 0, frame 1, frame 2, frame 3. Otherwise, when an acknowledgement comes back from the other side, the sender does not know which frame is acknowledged. Which frame is acknowledged. Okay. So, if you look at the frame format, let's say this is frame, this is header, this is payload, this is header, this is payload. So this header has a field called sequence number. Sequence number. So say, let's say the sequence number is a 3-bit sequence number. That means the sequence number can be 00 to 111. That means frames are numbered using a 3-bit number. Frame 0, frame 1, frame 2, frame 7. Then the next frame will be frame 0, frame 1, frame 2, frame 7. Note that this frame 0 is different from the other frame 0. Okay, so later we see that how we can avoid confusion about this frame 0 and the frame 0 in the next window. Okay. Is it clear? That's what is written here. Sequence number is bound by k bit field. That is k bit sequence number, which is sent as a part of the header in the frame. They are numbered modulo 2k. That means 0 through 2 raised to the power k. So if k is 3, it is 0 to 7. Is that fine? So when the receiver acknowledges, it has to tell which frame it is acknowledging. This is the notation. It says ACK-N. The message means this is another frame. Acknowledgement is also another frame, but it's a short frame. Okay, so 1 bit or few bits may indicate that it's an acknowledgement frame. It's not a data frame. Okay, and the notation is either we say ACK-N or RRN. RR means receiver ready. RR means receiver ready. Now, you need to be careful in understanding this notation. When we say RRN or ACK-N, this does not mean that it is acknowledging frame number N. No. RRN, which stands for receiver ready N, that means receiver is ready to receive frame number N onwards. That means receiver is acknowledging frame number N-1 and the earlier frames. Okay. That means if you say RR5, that means receiver is ready to receive frame number 5, which implies that, or it implicitly acknowledges that frame 4, 3, 2, 1 of the previous frames were acknowledged. So this is called cumulative acknowledgement. That means it does not need to acknowledge each frame separately. It sends one frame, RR5. That means it says I received up to 4. I am ready to receive from 5. That's what it means. Is that clear? Don't get confused. RR5 does not mean that it is acknowledging frame number 5. RR5 does not mean that it has received 5 frames. No. RR5 means it is ready to receive frame number 5 onwards. Implicitly, it is acknowledging frame number 4 and earlier frames. So this you need to be clear. Until the examination, I see that several students get confused. Okay. Now let's look at how it works. Very interesting method. You will also understand why it is called sliding window. Okay. So there is a sender, and we set size as k, W. Let's say frame is numbered with k sequence, k bit sequence number. So let's say frames are numbered from F0 to F7. Let's say we assume W as 7. Later we will understand W cannot be 8. Maybe we look at one example in the tutorial. Okay, window size cannot be 8. Okay, it can be up to 7. So because you can ask, frames are numbered 0 to 7. There are 8 different numbers. Why frame is restricted to 7. If we allow frame to be 8, then there is, in some cases, there will be confusion when the acknowledgement comes, whether this acknowledgement is for frame 0 in the current window or frame 0 in the previous window, because frame numbers are cycling through 0 to 7, 0 to 7, 0 to 7. To avoid confusion, we keep frame window size W as 7, not 8. Okay. So what the sender does is, whenever it transmits a frame, it decrements the window size by 6. So conceptually we say, when a frame is sent, window shrinks by 1. Don't think that there is a window inside. No. Window means there is a simple program. Yeah, there is a count. It's a count kind of thing. There's a variable W which is initialized to 7. W equal to 7 means window size is 7. Current window is 7. It means that the sender is permitted to transmit up to 7 frames without waiting for an acknowledgement. That's the meaning. Since it has sent out 1 frame, window will shrink. That means a number W will become 6. It's permitted to transmit only 6 more frames because it has already sent 1 frame. It has not yet received an acknowledgement. Then when it transmits another frame, window size will become 5. Window size will become 5. Now let's say it transmits another frame, the window size will become 4. Let's say now it receives an acknowledgement for 1 frame. When it receives an acknowledgement, this 4 will become 5. What does it mean? The current window is 4. That means it has transmitted 3 frames. It's permitted to transmit 4 more frames. Now it receives an acknowledgement. That means it's permitted to transmit 1 more frame. That means 4 will become 5. Is that okay? So because basically it defines, okay, how many outstanding frames can be there. How many frames can be transmitted without waiting for an acknowledgement. Okay. So whenever an acknowledgement is received, window expands by 1. That means the window count W is incremented by 1. That's all. Usually the sender keeps the frames in buffer until they are acknowledged. Why? Any reason? Can you guess? For retransmission. If there is any error, okay, something is missing, it should retransmit it. Okay. So for that purpose, okay, when a frame is transmitted, still it is kept in the local buffer until it is acknowledged. Now what the receiver does is the same way. Receiver also keeps a window of size W. Again, it's a simple variable. So what the receiver, this is the receiver, okay, initially W is equal to 7. When it receives a frame, it becomes 6. Okay, now initially W equal to 7 means it can receive up to 7 frames without sending out any acknowledgement. Okay, now it receives a frame, then W becomes 6. That means it can expect up to 6 more frames. Okay. Let's say it receives another frame, that is now W equal to 5. It receives another frame, W equal to 4. Then W equal to 3. Let's say it transmits an acknowledgement. When it transmits an acknowledgement, window will expand. 3 becomes 4. Okay. Is that fine? So basically, so initially W equals 7 means it can receive up to 7 frames. Then 6 frames, 5 frames, 4 frames, 3 frames. Now it transmits an acknowledgement. It helps the sender to expand the window by 1. That means it can receive 1 more frame. Compared to W is equal to 3, now it is W equal to 4. Okay. So that's what it says. Window size indicates the maximum number of frames that could be received. Whenever a frame is received, window shrinks by 1. That means W is decremented by 1. Whenever an acknowledgement is sent, window expands by 1. It lets the sender to send 1 more frame. So it can expect 1 more frame to receive. Is that fine? It keeps the buffer, the frames which are received, but acknowledgements have not yet been sent. Okay, as soon as a frame is received, it may not send the acknowledgement immediately. Okay, it has to process this. Okay, maybe these frames need to be sent to the next higher layer, or it may have to be sent out to the next link port. Okay, so when the processing is done, whether it's ready for transmission on the other side, or when it is passed to the higher layer, okay, then it will send an acknowledgement. So until the acknowledgement is sent, it keeps the frame which are received in the buffer. Any doubt? So let's look at an example illustration. So this shows the sender window. So there's a receiver. The bottom figure is that corresponds to the receiver. Okay. And you can see that the frames are numbered from 0 to 7, 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7, etc. Okay. So at a given instant, this may be the state of the sender. What it says, you can see there's a window. This is the window. So what is the size of the window here? 1, 2, 3, 4, 5. W equal to 5. The window size is 5. Just an example, okay? And you can see that there are two numbers, 6 and 7, written here between one edge of the window, and there is a vertical bar here. So what do they indicate? 6 and 7. These are the frames buffered until acknowledged. That means frame number 6 and 7 were sent out to the other side, but the acknowledgements were not received yet. Okay? So this is what it indicates. This W equal to 5 indicates that frame number 0, 1, 2, 3, 4 can be sent out without waiting for any acknowledgement. That's what it means. Okay? Let's say when a new frame is sent, what's the next frame to be sent? 0. If this frame is sent, then window will shrink, something like this. Okay? That means it has sent out 670, no acknowledgement received, so it's permitted to send 1, 2, 3, 4. Whenever an acknowledgement is received, this will expand from this direction. Okay? When an acknowledgement is received, let's say acknowledgement for 6 is received, this will expand by 1. This vertical line will come here. Is that fine? Similarly, look at the receiver perspective. Okay, for this example, the receiver and sender looks the same, but in practice may not. Okay? So here also W equal to 7. The total size is 7, but the current state is W equal to 5. So here the meaning is this. There is a vertical bar here. There are two numbers, 6 and 7. This indicates that frame number 6 and 7 were received, but the acknowledgement were not yet sent. And all the numbers inside the window, 0, 1, 2, 3, 4, they indicate that they are the frame numbers which could be received from the sender. Even if it does not send the acknowledgement, it can expect 0, 1, 2, 3, 4. Okay? What happens when a frame is received? Whenever a new frame is received, this will shrink here. When an acknowledgement is sent out, this will expand from the other side. So when it shrinks from one end, expands from other end. Shrink, expand, shrink, expand. So this is something like sliding. It's a sliding window. Again, this is just for conceptual understanding. Okay, it moves like a window. But in terms of implementation, it's simple variable. W is a count, some variable. This is manipulated, incremented, decremented, incremented, decremented. Okay, and the window is something like a set or array, 0, 1, 2, 3, 4, 5. This could be a simple array or simple list or the set in the program implementation. Let's look at another example. Okay, so this considers even the cumulative acknowledgement. So initially W equal to 7, W equal to 7. So what does this window imply? Sender is permitted to send 0, 1, 2, 3 up to 7. Receiver is permitted to receive 0 up to 6, 0 to 6, because the window size is 7. Okay. Again, this is one example. Okay. Let's look at the state of the window. Frame 0 is first transmitter, and this will be updated. We are not showing the state of the window in between. Okay. Let's say we are interested to know what is the state of the window after the transmission of 0, 1, 2. So 3 frames are transmitted from the sender. So from the sender side, it should shrink. The window should shrink by 3. Window size should be decremented by 3. So you can see that immediately after the transmission of the third frame, this will look something like this. Here window size is 4. Window size is 4. You can see 3 frames, 0, 1, 2. That means it has already sent a transmitted frame 0, 1, 2, but acknowledgement not yet received. And something is inside here, 3, 4, 5, 6. So 4 more frames could be transmitted. 4 more frames could be transmitted without waiting for any acknowledgement. Okay. So if it has 4 new frames, it can transmit it, no problem. Is that fine? So after receiving the 3 frames, what is the state of the receiver? Again, whenever a new frame is received, the window state will be updated. I am not showing it here. After the 3 frames are received, this window will shrink from the left side by 3. So W becomes 4 here. So meaning here is this: 0, 1, 2. These 3 frames were received. Okay, but acknowledgement not yet sent. It can receive 4 more frames from the other party. So it should be ready to receive 4 more frames, because sender can send up to 7 frames. Okay. Now it transmits at this time an acknowledgement RR3. RR3 is a cumulative acknowledgement. Cumulative acknowledgement. That means receiver ready to receive frame number 3 onwards. That's what it says. That means when it says it's ready to receive frame number 3 onwards, it implicitly acknowledges frame number 2 and the earlier frames. What are the earlier frames? You can look at this. These are the frames which were received, 0, 1, 2. That means it acknowledges all the frames, all the 3 frames. Is that fine? Because it has acknowledged 3 frames, the window will expand by 3. Now window size is 7. Window size is 7. And you can see this vertical bar has moved here, because there is no frame which is yet to be acknowledged. All frames have been acknowledged. Now what happens here at this sender side? When RR3 is received, it checks the state. That means there are 3, 0, 1, 2 inside this, which are yet to be acknowledged. Now the receiver says RR3. Receiver is ready to receive from 0, 3 onwards. So receiver is acknowledging frame number 2 and the earlier frames. That means it's acknowledging all the 3 frames. So since it acknowledges 3 frames, the sender will expand by 3. So you can see this has expanded by 3. So W becomes 7, and you can see this vertical bar has moved here, because all the frames which have been transmitted by the sender, okay, have already been acknowledged. Any doubt? Now let's look at some few more scenarios. Again, we are not looking at all possible scenarios, but some scenarios. Now next frame sent is frame number 3. Frame number 3. So what is done here? When frame number 3 is sent, when frame number 3 is received, so it receives this frame, then it transmits an acknowledgement here. This acknowledgement is RR4. So after receiving frame 3 and sending an acknowledgement, okay, this will be something like this. Because when it receives frame 3, this will move here. This vertical bar will move here. When it sends an acknowledgement, this will expand by 1. Why it expands by 1? Because RR4 implies that it's acknowledging frame 3 and earlier frames. But according to this state, earlier frames, there are no earlier frames, only frame 3 it has received. Okay? So it implicitly acknowledges only one frame. So it expands by 1. That means W becomes 6, then W becomes 7. Okay. Now this shows the state where 3 more frames are sent. Frame 4, 5, 6. Okay. After these 4 frames sent from the sender, the state will be something like this, because 3, 4, 5, 6 are sent. So window shrinks. Now window becomes 2. Window becomes 3. Window becomes 3. There are 4 frames which are here. Okay. Now at this time it receives RR4. So RR4 means what? The receiver is ready to receive frame 4 onwards. So it's acknowledging frame 3 and earlier frames. So according to this state, frame 3 and earlier frames, that means only frame 3. So only one frame is acknowledged. Note that even though it is called RR4, it is acknowledging only 3. Since only one frame is acknowledged, it will expand by 1. So W equal to 4. And this vertical bar will move by 1 position, because 3 is acknowledged here. Is that okay? Now at this time, it receives 3 more frames after this, 4, 5, 6. So when these 3 frames are received, this will shrink by 3. So W becomes 7. So 4, 5, 6 will be here in between the vertical bar and the window, which indicate that these 3 frames were received but acknowledgements not yet sent. Any doubt? Yes?
So the receiver is not send the acknowledgement one by one. It sends the, like process the first 3 frames together, then it sends the
Okay. So in this example, sometimes it acknowledges after receiving 3 frames, sometimes it acknowledges after 1 frame. Okay. So in practice, the receiver need not acknowledge every frame. Okay. So it will acknowledge whenever, let's say, the frames are processed by this layer and maybe it has passed it to the next layer or to the outside, the other next link. Okay. Only then it transmits, okay, acknowledgement. So sometimes it acknowledgement for 1 frame, sometimes it also acknowledges multiple frames. That's why we call it as cumulative acknowledgement. So this shows some scenario, okay. Okay, so whatever I explained here in illustration and this is only a key idea underlying the protocol or sliding window protocol. Okay, there could be some enhancements or there could be some variants of sliding window. Okay, but you can easily understand how it works. For example, we may introduce a new kind of acknowledgement called receiver not ready. So receiver not ready. See, for example, we can enhance the protocol. We can add new features. See, for example, receiver can acknowledge frames without permitting further retransmission. Receiver can say, okay, I received these frames, but I'm not ready to receive any new frame. Okay? So what's the difference? Let's say RR4. RR4 means it is ready to receive frame 4 onwards. That means it's acknowledging frame 3, 2, 1, etc. the earlier frames. Okay. after seeing RR4, the sender can adjust the window, it can transmit more frames. But RNR, let's say RNR4 means it is acknowledging the receipt of the previous frames, 3 and earlier frames, but it's not ready to receive frame 4 onwards. Okay, that means as far as sender is concerned, it can record that these frames have been acknowledged, but it should not send new frame. For some reason, it's not ready to process new frames. So what happens when it is ready to receive new frames, the receiver will send another acknowledgement, this is a normal acknowledgement, to resume. That means after some time it may say RR4. Okay. So depending on the requirement and the applications, we can introduce new features. Then another interesting enhancement is piggybacking. Okay. If the communication is duplex, it's likely that particularly in the wide area environment connecting switches and the routers. So let's say this is A, let's say this is B. The duplex communication could be implemented by maybe 2 fibers, one on either direction. Okay. Duplex means A sends to B, same time B can also be, B also can send to A. So A is a sender for some traffic for which B is the receiver. B is a sender for some other traffic for which A is the receiver. Okay. So what can be done is this. When A sends, let's say A sends a data frame. What B does, B sends an ACK frame. Okay. Instead of sending an acknowledgement frame, what B can do is, B sends a data frame and it can indicate here it is, let's say, RR5. Okay. So every data frame has a header. Am I right? And some bits in the header can be used to acknowledge the other party. So A sends a data frame to B. B can send a separate acknowledgement frame, let's say RR5, or if B has some data to send to A, some other data frame, okay, it can send that RR5 as part of its data frame. What's the advantage? It avoids sending 2 frames. It sends just one data frame because it has some data to send to the other one. So it attaches acknowledgement as part of the data frame itself. That's called piggybacking. Is it clear? Okay. Now there can be few cases. If there is no data to send, that means A sends a data frame to B. B wants to send an acknowledgement. If B has no data frame to send back to A, it can send a normal acknowledgement, separate acknowledgement. Okay, that can happen. But let's say B has some data to send, but B has not received any new data frame from the other side. Then it can simply repeat the previous acknowledgement. Let's say A has sent some frame, B has sent RR5. Okay, but B is sending new data frames. A is not at all sending anything. So B can repeatedly say, I am ready to receive 5. I am ready to receive 5. Okay, because the acknowledgement field RR5, it can embed inside the header of its own data frame. So this kind of mechanism is called piggybacking. So it uses this data frame to carry the acknowledgement for the data frame which it has received from the other side. Any doubt? Any doubt? Okay, next topic is error control and reliable retransmission. So we now extend the flow control to include errors. In the previous examples, we don't consider errors at all. We assume that every frame safely reaches the other side. So what happens if there are any errors? Okay. So to deal with that, we need to have a mechanism to detect or correct errors. Error detection is done by CRC at the link level, which we have already seen. Okay. CRC division method to detect whether there is any error or not. Although theoretically we say can we correct an error or not, as I said before, practically it's not a feasible or not a good solution to try to correct error for every packet or frame. Okay, it's almost impossible or extremely difficult to carry out this. Instead, if there is an error, you drop the frame. Okay, if the protocol supports retransmission, then the receiver will request the sender to retransmit it again. Otherwise, just drop the frame. That's all. We deal with two kinds of frames. As I said before, lost frame and damaged frame. Damaged frame means receiver can recognize that there is some frame. That means it can do some CRC calculation and other things. Okay. And CRC fails means there's a damage or there's an error. Lost means the noise burst heavily affects the frame to the extent that the frame is not recognizable by the other side. That's what I said. During propagation, if a frame is heavily damaged, the other party may not even know that it's receiving some signals part of some frames. Okay. So we need to deal with both. Okay. Sometimes some approach, some policy may solve both, whether it's a lost frame or damaged frame. Okay, the same protocol will work. Okay, sometimes we can differentiate. Okay. So to deal with this error and retransmission, a number of mechanisms should be in place to deal with this. What are those? One, error detection. The protocol or the network should support error detection, and there is a mechanism which we have already seen, positive acknowledgement. Positive acknowledgement means it is acknowledging that some frames have been received. So we use ACK or RR. Both are same. Sometimes we say ACK3, sometimes we say RR3. That's fine. Both refer to positive acknowledgement. Okay. Next, retransmission after timeout. There is a mechanism called timeout. So why there should be a timeout? Okay. Let's say the receiver receives a frame and detects an error. It can send a negative acknowledgement to the other party. Hi, I am rejecting frame number 3. There is some error. Retransmit it. So no problem. After receiving this, sender will retransmit frame number 3. But the question is, what happens if that negative acknowledgement message is lost? Okay, A sends a frame, that is there are some errors. So B, okay, sends a negative acknowledgement to A that something is missing or something is rejected. Okay, so now the question is, if that negative acknowledgement is not received by the other party, what happens? Sender is waiting for something from the receiver side. Receiver has sent something which is lost, so nothing happens. Okay, so both of them cannot move further. Okay, A will stop transmitting, B also expecting something from the other side, nothing is happening. So how long they can wait? How long they can wait? Infinite times? No, it cannot. So we define a timeout period. So certain period of time it waits. Within that period of time, there's no new event happens. Okay, let's say it does not receive any acknowledgement within the timeout. Then it has to do some new, it has to act. It has to act. Okay, let's say you send a message to your friend. It's just some casual image, you don't bother whether it's responding or not. Okay, let's say an important message. You are sending a message to your friend. You expect some acknowledgement or you expect some reply. You don't get a reply. Waiting for a few minutes, hour, day, no. So then what do? You are waiting for the reply? No, you cannot get it. You should do some extra thing. Then you have to probe. Maybe you may have to call. Hi, I sent some important message. Did you receive it? Can you reply for that? Am I right? So there's a timeout. It depends. Okay, how long you can wait. So if there's no such timeout mechanism, then both of them cannot proceed, sender and receiver. The negative acknowledgement messages which we use here, okay, they are basically NAG, negative acknowledgement, or reject, selective reject. So there are three kinds of negative acknowledgement we are looking at. So the meaning would be clear when we look at the actual protocol. Okay. So all these mechanisms together, we call this as ARQ. ARQ stands for automatic repeat request. That means there is some error, it requests other party to repeat or to retransmit. So this whole mechanism happens automatically. So we call it as automatic repeat request, ARQ. And any protocol which implements this will also be tagged with ARQ. So accordingly, we have stop and wait ARQ, stop and wait ARQ, which is an extension of stop and wait protocol to deal with errors as well. And we have sliding window based ARQ, but here we have two types, two different ARQs for sliding window, one called go back N, the other one is called selective reject. So the difference would be clear slightly later, okay, but both are based on sliding window control. And the maximum window size for go back N is 2 raised to the power k if k is the sequence field. That means if you use 3-bit sequence number, frames will be numbered from F0 to F7, but W can be less than or equal to 7. That's why in my example or illustration, I might have used W equal to 7. I can use W equal to 6 or 5, it doesn't matter, but I should not use W equal to 8. Okay. Why? If W equal to 8, there will be some confusion, there will be some problems, which we look at in the tutorial. Okay. Similarly, for selective reject, you just need to remember at this stage, at this point, that it's also based on sliding window, and the window size, maximum window size can be 2 raised to the power k minus 1 here, where k is the sequence fold. That means here the window size can be up to 4. 2 raised to the power, you see that k minus 1 is in the exponent, k minus 1. Again, it has its own reason why it restricts the window size. The typical window size depends on several factors, whether what is the distance or the length of the link, okay, and what is the capacity of the link, okay. So it depends on few factors. We will slowly look into the details, but before that, just let's have some rough idea of the window size in two cases. Let's consider the case, okay, where the link capacity is quite high and it's a long distance link. You consider a link capacity is high, that is high speed link. When the link bandwidth or link capacity is quite high, what is the transmission time? Will be short or long? When the capacity or bandwidth increases, the transmission time will be short. You can quickly transmit a bit. Am I right? Okay. So that means you have a window size. If the window size is small and your bandwidth is high, that means you quickly transmit a frame. Am I right? So if your window size is small, let's say W, the sender is allowed to transmit up to W frames before waiting for an acknowledgement. Okay. So if the transmission is faster, it will quickly exhaust the window. Okay. Let's say the link is a long distance link. Long distance link means the acknowledgement time will be quite long. Okay. Because the last bit has to travel to the other side. Then the receiver has to send the acknowledgement. It has to travel back to the sender. Okay, so if it's a long distance link, it takes more time for the acknowledgement to come back. Okay, so we want to keep the window non-empty until the acknowledgement comes back. If the window is quickly exhausted before the acknowledgement is received, then sender has to wait for a long time. Am I right? Let's say the link is high-speed link, so means it's quickly transmitting. So window size, let's say window size is small, we fixed at just 7. So 7, 6, 5, 4, 3, 2, 1, over. But acknowledgement is not received because it's fast in transmitting. We don't want that to happen. Ideally, we want the window to be non-empty. Still, window can accommodate something when an acknowledgement is received. Okay, then we can continuously transmit without any problem. Okay? So for the case of high-speed link, long-distance link, we can have a bigger number or larger window when compared to a low-speed link. If you keep smaller window, we will quickly exhaust. So to avoid that, we keep a larger window. Okay, now we are ready to look into the protocol. We start with stop and wait ARQ. Okay. So as the name says, it uses stop and wait flow control. Okay, just to recall, sender sends a frame, wait for an acknowledgement, then sends the next frame, wait for an acknowledgement. Same thing. Okay. Now what happens if the frame is damaged or lost? In both cases, the receiver can simply discard it. That means the receiver simply can keep quiet. Okay, if it receives a damaged frame or is a lost frame, that means it has received some bits here and there but doesn't even know what it is. Okay, so the receiver can simply keep quiet. It doesn't need to send anything back to the sender. So there is a timeout time period. So sender will wait for certain time period. How long it can wait is a design issue. We know that how much time it will take for the frame to go there and the acknowledgement come back. So roughly a number close to that can be assigned as a timeout value. So it's because the receiver is not sending anything back to the sender, so the sender will time out because it has not received anything. If sender times out, okay, it can retransmit the frame. Same frame will be retransmitted. Now look at this illustration. So this case, stop and wait is the same as the case of sliding window with window 1. Window size is 1. That means it's permitted to send up to 1 frame without waiting for an acknowledgement. As soon as it sends 1 frame, window becomes 0. Am I right? So this is something like 1. Now it uses a 1-bit sequence number. That means frames will be numbered frame 0, frame 1. Frame 0, frame 1. Frame 0, frame 1. Frame 0, frame 1. Okay. So what's happening here? Look at this. A is the sender. It transmits a frame. It transmits frame number 0. And upon receiving this frame, B transmits a small acknowledgement frames. It sends ACK1. ACK1 is the same as RR1. So what is ACK1? ACK1 means the receiver is ready to receive frame number 1. That means it acknowledges the previous frame. Frame number 0 is acknowledged. So when it's received here, it transmits frame number 1. Okay, then it sends ACK0. ACK0 is RR0. That means the receiver is ready to receive frame number 0. Okay, it sends frame 0. Let's say this is lost. Maybe it could be damaged also. Okay. So you can see that during this period, the receiver is not responding with anything. So the sender times out. When it times out, the same frame 0 is transmitted again. So it's retransmitted. So after receiving frame 0, it sends ACK1. Then frame 1 is received, it sends ACK0. But in this case, ACK0 or RR0 is lost. Okay. So as far as sender is concerned, it has sent frame number 1. It has sent frame number 1, but it has not heard anything. It has not received anything from the other side. But actually, as far as receiver is concerned, it has already sent out X0, but which is lost. So what the sender will do here, let's say times out. When it times out, what it understands is, or what it knows is, it has sent out frame 1, it has not received an acknowledgement. It can happen due to 2 reasons. 1, the frame 1 was lost. Reason 2, the acknowledgement was lost. Am I correct? But it doesn't want to take a chance. What it does is, it simply retransmits frame 1. So same frame 1 is retransmitted. Okay, you take it, frame number 1. Now, what the receiver receives, earlier it received frame number 1. That means there's a frame with sequence number 1. Now it receives another frame with the same sequence number 1. Okay? So it should know that it's a duplicate frame. Just because the frame number is same, we cannot say it is duplicate frame, same frame. Okay? Is that fine? So how does it know it's a duplicate frame? Very simple. What receiver knows is that it has sent acknowledgement 0. The receiver has sent acknowledgement 0. That means the receiver is expecting frame number 0. It is expecting frame number 0, but it is receiving frame number 1. Then it understands that there is some confusion on the other party. It is a duplicate frame. So duplicate frame means this frame will be discarded, will be thrown out. That's all. It will be dropped. That is what should be done with that particular frame. Any doubt? Yes? Okay, we have already seen that stop and wait, okay, is simple to implement, but in terms of resource utilization or link utilization or bandwidth utilization is poor. Okay, so how do you define link utilization? Later we derive some simple expression, but just look at quick definition. It's defined as the ratio between the actual time spent transmitting a frame and the total time the link is engaged. That means you take this is frame 0. This is the time when the first bit of frame 0 is transmitted. This is the time when the last bit of frame 0 is transmitted. So it has to travel to the other side. Then here is the acknowledgement sent by the receiver. There is another TP time unit when the acknowledgement comes back. So it transmits frame number 1. Okay. So let's say this is TF. So total time it's using or it's engaging the link for TF plus 2 TP time, out of which, so this is the total time, out of which only TF is the useful transmission, because the remaining period it is just waiting. So during this period it's not using the link for transmission, but it's holding the link. It's not transmitting anything. Okay? So the ratio between the actual transmission over the total time which is holding the link is the utilization. Is that fine? Anyway, later we derive some simple expressions. So let's move on to the next protocol. Let's quickly look at the principle of this before we wrap up session. So we start with go back N, which is based on sliding window. Okay, I don't want to repeat how sliding window works. Okay, so now we look at a specific case of error. When there is no error, the receiver will send ACK or RR, RR3, ACK3, okay, RR5, whatever it is. Okay, if there is any error, what should be done? If there is any error, what should be done? So let's look at few cases, and you will also understand why it is called go back N. Okay. Now look at this case. I mean, the best way to learn the concept is look at some example scenarios. Okay. Receiver receives frame I. let's assume that I is equal to 3. Let's say this received frame number 3. Frame number 3. So assume that the frame is damaged. After receiving frame 3, when it does CRC testing, it finds that okay, CRC test failed, so there is an error. Okay, so if there is an error, what it will do is it will send a reject I. That means reject 3. It sends reject 3. Okay. So at this time frame 3 was sent. At this time frame 3 was received. At this time reject 3 was received by the sender. In between, the sender might have transmitted, let's say, frame number 4 and frame number 5. Before the sender receives reject 3, because it's window based, it might have transmitted frame number 4 and frame number 5. Okay, so frame 4 is received here, frame 5 is received here. What the go back N will do is, it's something like quite adamant. Okay, it received frame 3, it was damaged, and it will not accept any new frame until frame 3 is correctly received. Okay, so that means this will not respond to frame 4 and 5. This will simply discard these two frames. It has received frame 3, damaged, it has asked for a new frame. Any new frames received, that will be simply discarded. Okay, it will not respond anything back to the sender. Okay. What the sender will do, sender has received reject 3 here, but it has transmitted until frame number 5, but it knows that they are following go back N. Okay, so it will retransmit frame number 3. It retransmits frame number 3. Now what is the next frame to be transmitted? Frame 4, 5, it has already transmitted. Okay, now the next frame to be transmitted is frame 6 or frame 4. For go back N, it knows that the receiver will not accept any new frame until frame 3 is correctly received. So it will retransmit frame, it will repeat F4 and F5 also. Even though it has already sent F4, F5, that may be a good frames, they may be a good frames, but still it will repeat 4 and 5. That means when the sender comes to know that frame 3 was not correctly received, it should go back to frame 3 and it will continue from there. Is that clear? Why it is called go back N? It goes back to 3, it continues 4, 5 again. Even though it has already sent 4 and 5, it will repeat 4 and 5. So after receiving frame 3, then the receiver will happily accept frame 4 and frame 5. Then it might send an acknowledgement. Any doubt? Okay, let's look at one more case. Now, this is the case deal with a frame which is lost. It's a lost frame. Let's say frame I is lost. So in the previous case I equal to 3, maybe let's assume that I is equal to 3. Frame I is lost. That means frame 3 which is not at all received. Then frame 4, frame 5, etc. Okay? Frame 2 is received. Frame 1 is received, but frame 3 is lost. Frame 3 is lost. That means the receiver receives frame 2 here, receiver receives frame 2 here, frame 4 next. The receiver did not receive frame 3. The receiver did not receive frame 3. So it knows that it is out of sequence. After 2 it receives 4. That it infers that 3 was lost. Okay. So after it infers 3 was lost, it will send reject 3 here. How does it know it is lost? Because it received F2 and F4 out of order. After 2 it has received 4. So will it accept 4? It will not accept 4. Will it accept 5? It will not accept 5. Because it knows that 3 was lost. It's looking for 3. So what the sender will do after receiving 3, it will retransmit frame number 3. It follows go back n. So it will go back to 3. It will start from 3 again. So 4, 5, all are repeating. All are repeating. Okay? Any doubt? Now the question is, here we assume that frame 2 was sent, 3 is lost, then frame 4 was sent. In that case, it can find out. It is out of sequence. Okay? What happens if frame 3 was sent, frame 4 lost, but there are no new frames sent from the sender? Frame 3, frame 2 was sent, frame 3 was lost. Frame 3 was lost. Got it? But it's not sending any new frame. The sender is not sending new frame. Why sender is not sending a new frame? It doesn't have new frame to send. Or let's say window is exhausted. It has exhausted the window. So it's not permitted to send any new frame. So frame 3 was the last frame. It's not sending any new frame. So what happens in that case? Receiver receives 2. It's not receiving any new frame. It may keep quiet. It might keep quiet. Okay? So there is a possibility. So in that case, the sender will time out. Sender will time out. Because nothing is happening from the other side. Okay? If it receives some positive acknowledgement, it will expand. Okay? But if nothing happens, something was lost, whatever it sent, then after some time, it will time out. Okay? So it doesn't receive anything from the other side. When it times out, the sender has to probe, hi, I'm not hearing anything from you for a long period of time. What's happening on your side? Can you tell me what is it you are expecting from me? So the sender sends a special frame, which is called receiver ready frame, which is a command frame. It's not a data frame. Okay, and that command frame has some header field, and one of the field bit is called P bit, probe bit, that will be set to 1. So when this frame is received by the receiver, it knows that, okay, this is not a data frame because this particular bit, P bit, is set to 1. So the receiver knows that sender wants to know what has happened, which frame the receiver is ready to receive. Okay, so when such command frame is received, the receiver will send a new RR frames. Okay, let's say it's expecting I, frame number I. Then at that time it will send RRI. Hi, I am ready to receive frame number I. Is that okay? Any doubt? Any doubt? Okay, let me stop here. We will continue maybe on Wednesday. So what we do is we continue for some time. Tutorial 2 problems I will post. Then after I complete this, maybe I do tutorial 2. Or let me decide whether I do tutorial 2 then continue lecture. Okay, anyway, we will have lecture or tutorial this Wednesday.